Welcome back to the AI Research Roundup. I am your host, Alex. Today, we're looking at a paper from May 19th, 2025, Thinkless, LLM learns when to think. So, reasoning language models. These are LLMs capable of extended chain of thought reasoning, which is where the model explicitly thinks step by step through a problem. They're great for complex tasks, but often inefficient for simpler ones. This paper introduces Thinkless, a framework that empowers an LLM to adaptively choose between detailed reasoning or a concise answer. It's trained using a reinforcement learning approach featuring a core algorithm called Decoupled Group Relative Policy Optimization, or DeGRPO. And it's great to see that the authors have also made the code for this work available. So over on GitHub, you can find the Thinkless framework itself, along with scripts for evaluation and for that reinforcement learning training we just mentioned. They've also got installation guides and even some pre-trained models to check out. Alright, so this figure really illustrates how Thinkless works. On the left, you see a query comes in and the system makes an auto decision, choosing either a less than think greater than token for a long, reasoned response, or a less than short greater than token for a concise one. This decision is guided by the Decoupled Group Relative Policy Optimization algorithm. Then, the bar chart on the right shows the results. On benchmarks like GSM-8K, it predominantly uses the short mode, achieving high pass at 1 scores. Pass at 1, by the way, just means the percentage of problems where the model's first answer is correct. This really highlights the efficiency gains. Okay, so building on that overview, this diagram shows the training pipeline. It starts with RL data, queries and answers, feeding into a warm-up phase. Here, the system uses distillation, where the model imitates expert reasoning and non-reasoning models to learn to output those less than think greater than or less than short greater than control tokens. After a token is sampled, the response is generated and then gets a reward. For example, 1 for a correct short answer, slightly less for a correct long one to favor efficiency, and -1 for errors. This is all driven by Decoupled Group Relative Policy Optimization, which distinctly optimizes choosing the right mode and the accuracy of the response itself. Alright, so this table really puts that training to the test. It shows empirical results across several math benchmarks, comparing base LLMs, models always using short chain of thought, and hybrid approaches. We see pass at 1 accuracy, total tokens used, which indicates computational cost, and the think percentage for hybrid models. Thinkless, for instance, on GSM-8K used its thinking mode for only about 13% of problems, maintaining good accuracy with far fewer tokens than full reasoning. On the tougher AMY dataset, it smartly ramped up thinking to nearly 71%. And it's interesting to see other hybrids, like Router Q7B on GSM-8K, also achieving high accuracy with very low thinking percentages, underscoring the efficiency gains here. Okay, so these charts really drive home the difference in policy training. On the left, in chart C, we see what happens with a collapsed policy. It just defaults to using the short mode for 100% of queries across all 4 datasets. You can see its pass at 1 accuracy there, which is quite low for AMY 2024, for example. But on the right, chart D shows the learned policy of DeGRPO. Here, the model adaptively chooses between think mode, that's the dark teal, and short mode, the light gray, showing a much more nuanced and effective strategy, especially for datasets like Math 500 and Minerva Algebra. Okay, so we saw how the learned policy from Decoupled Group Relative Policy Optimization adaptively chooses between think and short modes. These graphs now dig deeper into the training process itself. Plot A on the far left shows what happens with a standard approach the paper calls Vanilla Group Relative Policy Optimization. Here, the number of think samples, in dark teal, just plummets, meaning the model quickly collapses into mostly using the short mode. But then, plots B, C, and D show our Decoupled Group Relative Policy Optimization. Remember, this version separates the learning for choosing the mode from learning to be accurate. And you can see in plot B a much better balance, with that characteristic U-shaped learning curve for think samples. Plot C shows short sample accuracy generally improving, and plot D reflects more all-correct short responses over the training steps. This really shows how decoupling those objectives prevents that mode collapse, and leads to more stable, effective training. Alright, so this table delves into that warm-up phase we touched on, specifically looking at the effectiveness of different supervised fine-tuning datasets. We're seeing pass-at-1 accuracy and token counts across benchmarks like AIM 2024 and GSM 8K. The long mode, where the model emulates a strong reasoner, consistently gets higher accuracy. For instance, 0.3067 on AIM 2024 with the larger OPE-NTH OUGHTS1M dataset. But as expected, this long mode uses significantly more tokens than the short mode. This stage really demonstrates the model's capability to learn both response styles effectively, which is foundational before reinforcement learning refines the actual decision making. Okay, so after that supervised fine-tuning warm-up, the model goes into reinforcement learning using decoupled group relative policy optimization. This plot here shows the impact of a specific setting within that, called the alpha coefficient, which is a weight that helps balance how quickly the model learns to select a reasoning mode. We're looking at the number of all correct short samples on the y-axis versus training steps on the x-axis. With a higher alpha, that's the dashed gray line at 0.5, the model starts producing these correct short answers much faster. A smaller alpha, the solid teal line, at 0.001, takes longer to get going, but eventually produces a similar number of correct short samples. This really illustrates how that alpha coefficient tunes a learning speed for mode selection. We've seen how that alpha coefficient helps tune the learning speed for choosing between reasoning modes. Ultimately, the Thinkless approach, with its decoupled group relative policy optimization, shows we can teach LLMs to be more judicious, deciding when to engage in deep thought versus a quick response. This makes them more efficient and adaptable, saving resources. Well, that's all for this AI Research Roundup. Thanks for tuning in. I'm Alex.